document, which is also an answer key for that SAM. So we're going to go through it, the raw document itself. We also have a couple of data sheets as well that are related to it. Okay, so I'm going to start off with those sample sheets, and also going to just take a quick peek in the chat box and say, okay, so, okay, I think you guys are all together there. All right, you can see me and hear my voice, correct, online? Okay, good. Let's go through those questions. Maybe that's a good preparation. Okay, let me put some Word document. Okay, so one of the things we start the semester with, which is kind of not obviously important, but turns out later on in the semester, it's really going to become kind of critical, is understanding the variable types, because the variable types determine what kind of statistical analysis you're going to do with those, what kind of tests you're going to use, what kind of procedures you're going to use, what kind of data you're going to collect, and so on and so forth. So it's deceptive. They don't look that important. It doesn't look that important, but it turns out that it's going to be pretty important. So let's take a look at this first problem, which covers that. This is similar to a homework problem for everybody, right? And what we're asking for here is what type of variables are each one of these things. SPSS only defines three basic types. Numerical, which it calls scalar, same thing, a scalar, number scale, right? Scalar. It doesn't bother to worry about like whether something is discrete numerical usually refers to something which is like a count, like it's a number, but it's usually an integer, and it's maybe a count, like for instance, how many siblings in each family, right? 3, 5, 7, or something like that. How many cups of coffee did you drink today, right? So, but SPSS just looks at it from the perspective of if it's numerical, even if it's discrete, doesn't really distinguish. You might be asked on an exam to distinguish between discrete and just other numerical variables, like blood pressure. Blood pressure could be, you don't normally see like 120/80 represents millimeters of mercury, but really, if you think about it, it really is not really 120/80. It could be 120.01/80.64. You know what I'm saying? It's a continuous scale. That's scalar. Right, we just tend to, since it doesn't need to be that accurate, we just make it look like it's a discrete reading, but it's not really. It's really scalar, so a little bit different. Okay, so let's take a look at this. Occupation: plumber, teacher, secretary, etc. What kind of variable? Categorical, right? Nominal or categorical. Basically, use those interchangeably. Social status: lower, middle, or upper class.
It's categorical.
It's categorical, but it's a special version of categorical, right? It's ordinal, right? Because lower, upper, middle, they even though they're names of classes, so it's nominal or categorical, they also have relevance in terms of one is larger or better or different than the others, right? However, it's not like a number scale where we know just by reading this that the difference between lower and middle is the same thing as the difference between middle and upper class, right? We know in the United States that the difference between lower and middle class is probably, the layoff, right? Difference between middle and upper class is really big, right? We understand that, right? So the difference, we see the order, we see it has order, so it's ordinal, right? But still, it's a form of categorical data. SPSS recognizes that. It differentiates between categorical and ordinal, right? It sees them as different kinds of variables. So we have in SPSS, we have scalar, we have ordinal, and we have categorical, right? Breaking it down a little further, categorical is, you can also have ordinal as well, which is SPSS really sees it different. And with numerical, you can have discrete also, which is really kind of the same thing, but a special version of it. Okay, statewide murder rate, number of murders per 1,000 population. Numerical, right? Scalar and numerical. County population size, number of people. Numerical. You could argue maybe it's kind of a count. It's an integer, it's kind of a count. But to tell you the truth, when it's a really big number like that, you'd normally just look at it as numerical. Population growth rate in percentage. Numerical, right? Okay, community size, rural, small town, large town, small city. Categorical, but special kind of categorical. Ordinal, right? Actually, yeah, I guess you would consider, yeah. If you look at why was it ordinal instead of categorical? There's two words there that make it ordinal. Community size. In other words, if you weren't looking at it from the perspective of community size, you were looking at it from the perspective of just breaking it up into groups, then that would have been just simply nominal or categorical. But the fact that you're specifically saying that that they're defined by community size says that there's some order there. Annual income, thousands of dollars per year, numerical. Altitude, attitude, altitude. Attitude towards affirmative action, favorable, neutral, unfavorable. Again, those categories, special form of category. Okay, at an emergency clinic, actually tell you the truth, I wonder, I think I would call that categorical because favorable versus unfavorable, I'm not sure, it's not greater. Yeah, I think we stick with categorical, not ordinal, right? Because they're selections, they're names of groups, but
It doesn't change.
yeah, it's not like good, better, best. Yeah, it's just different choices. Okay, so graphical summaries. Some of you saw this in lab. I think some in the homework assignment. Not all you got this in the homework assignment, but it's worth looking at because it could come up in an exam. Emergency clinic data was collected for 30 days on the number of patients arriving between 12 a.m. and 7 a.m. the night shift. At least one patient was treated every day. This produced a list of 30 numbers. Each number represents the number of patients treated on the night shift that day. Below is a histogram of the data. How many days were there more than 8 patients treated in the emergency clinic? This is kind of a particularly difficult version of this to work with. So here we have the number of patients treated per day, right? So 2 per day. That happened on 2 different occasions, 2 different days. How often did they get 3 patients, right? Well, that happened on 5 evenings, right? So the height, the frequency is the number of nights where you had that many patients, right? So it's a little bit hard to interpret this graph, but it's important that you first before you do anything, you get a look at the axes that are here and make sure you understand what they're asking about. Now, for instance, how many days are here? 30 days, right? So if we add these up, they should add up to 30. So let's do that. 2, 7, 7, 9, 10, 16, 18. 18 and 9 is 27, and 3 is 30. So that seems to work. Okay? So just as a check to wrap your head around it, you might want to do something like that just to make sure you understand what the graph is demonstrating. Okay, so at least one patient. On how many days were there more than 8 patients treated in this emergency room? Let's see, 7, 8. How many days did they have more than 8? What does it look like? This is 8 here. More than 8 would be 119. Yeah. So this represents 2 nights. This represents 3 nights. 3 nights. That's 6, 7, 8, 9 nights. Right. So if I ask you what percentage of the nights were there more than 8 patients, it would be 9 over 30. Okay. In fact, let's see if we ask that. We don't actually ask that. Okay. Below is a bar chart of body weights. Let me ask another question here. Okay, let me ask a second question here. Given that there were more than 8 patients treated, and that was going on behind me. Is that in this room? Yes. What's the speaker? Wow. Given that more than 8 patients were treated on a given night, what percentage of the time were there 11 or more patients? Given that there were 8 or more patients treated on the night, what percentage of those nights were there 11 or more patients? Okay, so how many nights were there 8 or more? That's 3, 6, 9, and 3 is 12, right? And, okay, and how many nights were there 11 or more? 3 out of 12. So 3 over 12, 25% of the time, right? 25% of those nights. What kind of probability is that? It's a conditional probability. Given that this condition, that there were nights that were 8 or more were treated, what percentage of those nights did we have 11 or more patients, right? So that's a conditional probability. It becomes important later on when we start talking about other things that involve conditional probability, such as the we have ghosts here, by the way. That's why I'm chuckling here. You guys that are online, I may not be able to hear that, but it sounds like we have ghosts here. Given that this has occurred, what's the probability that within those confines that this has also occurred? Conditional probability is going to come up again for, you guys remember, right? When you do your crosstabs for your diagnostic test, we have a conditional probability, which is important there, called positive predictive value. We'll come to that. In a study investigating causes of deaths among persons with severe, let me hang on a second.
You need to put the microphone.
I think that's it. I think I muted it now. Okay, I think that'll stop happening. Let me just check with you guys online. You're okay? Good. In study investigating the cause of death among persons with severe asthma, data were recorded for 5 patients who arrived in the hospital and stated respiratory rate. Breathing had stopped. The subjects were unconscious. Heart rates of 5 patients among admission to the hospital were 150, 40, 120, 136, and 104. Calculate the mean and median heart rate for these 5 patients. Discovering that the second patient's heart rate was misrecorded and should have been 140 instead of 40, recalculate the mean and the median of the corrected data. Does this mistake have a greater impact on the mean or the median? What do you think? Which one is more sensitive to outliers? The mean, because 40 is an outlier. He was the lowest. The mean is more sensitive to outliers. Yeah, let's demonstrate that. Let's actually do that, demonstrate that. We type in this actual data, 150, 40, 120, 136, 104. Okay, so I'm going to use Excel. I'm going to use the functions for average for the mean. Average of those 3 values and the median. Is that, okay, this is our mean. This is our median. Okay, let's change that 140 to that 40 to 140. Well, big change in the mean, right? Relatively little change in the median. Went to 136. Went from 110 to 130 versus just going up by about 6 in the median. Right? So bigger change in the mean. The mean is more sensitive to outliers than the median is. Right? So sometimes the median is a better measure than the middle is in a lot of cases. What else? What's another way of describing the mean? Right? The median rather? The median is literally the middle. Half of the values are below it, half of the values are above it. What percentile does it make it? It makes it the 50th percentile, right? So in other words, let's see if I can't do that here. We know we can use Excel to find a percentile, equal percentile, parentheses, it wants to know the list of numbers, comma, and the percentile we're interested in, which is the 50th percentile. And it turns out to be the same as the median. Right? So another way of calculating the median is the 50th percentile. And also, while I'm here, percentile, I want to calculate the 25th percentile, 0.25, and the 75th percentile. Okay, take the array of numbers, comma, and then that K represents, the little K that it's asking for right there represents the percentile, 75th percentile. Put it in as a decimal place, and that's 140. Okay, so now what is, this is the 75th percentile minus the 25th percentile. The area between the 25th and the 75th represents the middle 50% of the people in this study, in this sample or study of population. That's called the interquartile range, okay? And we know if we want standard deviation and so on, we can also do that, and the standard deviation, the variance, and so on and so forth. And we might have a little bit of that coming up. Yeah, main reason they ask you that question is that they want to show you the impact of removing an outlier on the mean and on the median. In 1986, the U.S. Federal Reserve is in the news right now, right? They just raised interest rates a 0.25%. And so that's probably going to happen quite a bit now. In 1986, U.S. Federal Reserve sampled about 4,000 households in it to estimate overall the net worth of a family, randomly selected them. Excluding some of the outliers of extremely wealthy individuals, they reported that the summaries 44 and 145,000. One of these was the mean, and the other was the median. Which do you think was which? Which do you think was the mean income? And which do you think was the median income? I would think that that's probably the median income, right? And this is probably the mean income. I'm guessing, right? I'm wondering about that. I don't like that. I'm going to take that out of there, make it a little clearer. If you include the super wealthy, right, then it's pretty clear that this would be the mean income because the wealthy people are pulling that way up, right, because they're making much, much more. And this is going to be the median income. It's a little bit more confusing if I leave that in, right, taking them out because there's a lot of people with very low incomes. So maybe it could have been around the other way around, but I don't think so. Okay, so the next one. Suppose that 3% of people in a given community of adults have attempted suicide. Suppose it also known that 20% of the community are living below the poverty level. If these two events are independent, what is the probability that a person selected at random from the community will have attempted suicide and be living below the poverty level? Okay, so when we talk about independent, we're saying that there's no association between one of these things and the other one. So for instance, let's say I asked, what's the probability of, let's say that I told you that 20% of the people in the United States have diabetes. Let me lower that. Say 10% of the population has diabetes. And 20% of the population is left-handed. Is there association between being left-handed and having diabetes? Probably not, right? I mean, that would be an interesting study to do, but probably not. So the probability that both would occur at the same time is probability 1 times probability 2. It's a multiplication. Okay, so it's going to be 20%, 0.2 times 0.1. So the probability is going to be 2%, 0.02, I guess, comes out, right? So that's 2%. So now let's take a look at this one. If the probability of being 3% of the population have attempted suicide, 20% of population is below the poverty level. What's the probability of randomly picking somebody and they're both below the poverty level and have attempted suicide? If they're truly independent, it's going to be 0.03 times 0.2. If they're not independent, And I'll bet you they're not independent, right? I'll bet you people below the poverty level, maybe they do commit suicide at a higher rate than people above the poverty. I don't have any evidence to prove that, but I'm just, my bias is saying that to me, right? Well, then it's not going to be 0.3 times 0.2, which is 0.06. It's going to be something else. What if you actually did this study and found out it was 0.09? What would that tell you? That would tell you that it's not independent, that there's an association between the poverty levels. So that's one of the ways you can test independence, is actually go out and sample a lot of people and see if it's really independent, if you really find the rate that you're expecting them to be when they're not independent. Okay, for the table below, we also did one of these in class, and I think maybe in an assignment and stuff like that as well. Refer to the table below. What proportion of women, this is the fraction of women that visit the obstetrician's office more than once?
2%.
Right. Yeah, let's see. Fraction of women, what fraction? Maybe more than one visit obstetrician's office, sorry, uncomplicated pregnancy. So 20% made no visits, 20% made one visit, 50% made two visits, and 10% made three visits. Okay, so what proportion made more than one visit? So that's going to be the people that made two visits and three visits. So what proportion of the population is going to be 60%, right? Okay, good. What proportion of the population made less than two? That's going to be 40%. What percent of the population made one or more? That's going to be all three of these. Okay. Given that a woman made a visit to the obstetrician, what's the probability that woman went there 3 times? Conditional probability. Given that a woman made at least one visit, right? Now we're only talking about these, because that's a condition that's satisfied, right? What's the probability that they went 3 times? Well, it's going to be 0.1 divided by 0.08, 0.1 divided by 0.8, which is, I think, 12.125, 12.5%. Okay, good. Okay, so just so we get through a lot of this, I'm rushing this a little bit so we get a lot of this stuff and get through as many of these as possible. Scores on the Psychomotor Development Index, scale of infant development, an approximately normally distributed mean with 100 and standard deviation of 15. A infant is selected at random. Find the probability that the infant's PDI score exceeds 103. So what is the standard deviation? It's 15. What does it mean? It's 100. I want to draw this out. I recommend that you guys do the same thing because it'll help you avoid making a mistake. Phew, excuse me. Okay. Gotta be close to flu season, time to get a shot, right? I teach a course at Rutgers, which is, I teach half the course. Another guy teaches the other 2 days. I teach 2 days of it. And it's an OSHA certificate course. And they, one of the things we cover is personal protective equipment and how to done it. A lot of these people, they're also learning about hazardous waste operations and protecting workers in hazardous waste operations, where they wear protective gear that's at the same level that you might, or even higher level than you might see doctors using for, say, Ebola or very dangerous communicable diseases. Okay, and I bring that up because they're very rigorous that I have put this stuff on and off and so on and so forth. And one of the things that they cover is like things about when you're going to sneeze, how to sneeze, and what you want to do to avoid communicating illness and so on and so forth. Sneeze, what is it now? You sneeze into your elbow or something like that rather than into your hands or something. They're pretty gross. And, but you'll notice, the reason why I say this, brought this up is because in a video showing doctors conferring in Nigeria in an outbreak, they wouldn't shake hands, they touch elbows instead of shaking hands. So at any rate, okay, so take a look at this. So we have a normal distribution. I mentioned it's a normal distribution. Normal distribution gives us a bell-shaped curve, right? And you guys remember the empirical formula? Right? The mean was 100. The mean score, for instance, is 100, and the standard deviation is equal to 15. Just as background, I put mu and sigma for mean and standard deviation. What does that tell you? This is I'm describing a population, not a sample. If it was a sample, I would put X bar, and I would put standard SD, standard deviation up there, right? So when I use Greek letters, it means I'm dealing with a population. If in case it comes up on an exam, this is called, when dealing with Greek letters and a population, it's called a parameter. When you're dealing with a sample, let's say something like X bar for mean, it's called a statistic, okay? So we know that 50% of the values are going to be under the mean, 50% of the values are going to be above the mean. In a true normal distribution, this is going to be symmetrical. You know, for instance, that if I were to draw values on either side of the mean, which are one standard deviation above the mean and one standard deviation below the mean, what is that area that's in there?
68%.
Good, 68%. You guys okay with this? Does this look familiar to you? Not new to you, right? Okay, semi-new to you, right? So we have videos on. You guys in 610, there's videos on this. I think the most recent class has some videos on this. If I'm wrong, it'll be. No, I'm sure it does, because next week we're going to be covering some other material, I think, as well. So anyway, it's 68%, right? And 95%, right? Two standard deviations above and below the mean. So that would be standard deviation of 15. That would be 115. So 68% of the children, the babies between 70 and 130, 70 over here, this 85. 95% of the babies between 70 and 130, 95% of the babies would have scores between 70 and 130. Above 130 would be only, what percentage do you think that is? Well, if this is 95% between here and here, and it's symmetrical, you have an area here, how much are you left with? 5%, so this is going to be 2.5%, exactly. Good, exactly. If I asked you what percentage of these children had PDA scores that were below 85, what would you say? Right, below 85. 85 is one standard deviation below the mean, right, between here and here, right? This is 68%. So I can see that this side's symmetrical, so this is 34%. This is 34%. So the mean below the mean is 50%. This is 34. What does that leave for the area below 85? 16%, exactly, right? So you can use the empirical formula, this idea of 68% and 95%, and then three standard deviations, 99.7%. Right? You can use that to get an estimate, wrap your head around what these areas represent. However, a lot of times we don't wind up with those exact numbers, like in this case. In this case, the mean is equal to 100, standard deviation is 15, an infant selected at random. What's the probability the score exceeds 103? Well, let's see what that's going to look like. That's going to look something like this. I'll get started fresh. 100, 103 is not very far above 100, okay? 103. So how many standard deviations above the mean is 103? Well, that's called the z-score. Number of standard deviations above the mean is called the z-score. You can calculate that. Z is equal to the value that you're interested in, 103, minus the mean over the standard deviation. If we were dealing with 115, it would be 115 minus 100, which is 15 over 15, one standard deviation. If we were dealing with 85, it would be 85 minus 100 would be minus 15. divided by 15 is -1, one standard deviation below the mean. But in this case, it's going to be equal to 103 minus 100 over 15. That's equal to 3 over 15, which is equal to 1 over 5, which is equal to 20%, 0.2. So the z-score here is 0.2. Well, now we need a way to figure out what area that represents. So that's when we go to our z table. Our z table. I tend to use, you can use the one in the book, of course, exactly the same way as the one I'm about to show you. Rest the table, it's going to be on your, it's on your various sources on Blackboard. On an exam, I make sure, let's see, keep misstating this. Rest the z table. Let's see if it comes up. There we go. There's the rest the z table. This is the z-scores right here on this column. And then for a z-score of -3, 3 standard deviations below the mean, would be represented by his z, whatever this value is. The area next to it is going to represent the area that's to the left of that. Same thing with a positive z-score. Notice a positive z-score is always to the right of the mean, so it's always going to be more than 50%. In fact, you can see the lowest number in this table is 50%. Right, but it's always, in this table, it's always going to be represented by the area to the left of the z-score. So if we wanted to look up the area for 0.2, we would look up 0.2 on the positive side, right? It's positive number 103 above the mean, right? 0.2. If it were 0.27, right? If we had another digit, we would go over here. This was 0.20, right? This gives you the third digit. 0.20, 2.21, 0.22. So it's 0.2. If it was 0.27, we would be looking for this number right here. If it's just 0.20, it's 57.93. For our purposes today, I'm going to abbreviate that 58%, right? 0.58. So this says that we know this area from 103 down is 58%, really 57, whatever it is. Right? What that, I believe that's what the problem is. That what the problem is? Let's find the problem again. What's the probability of infant short exceeds 103? Ah, that's a problem here, right? If it's 58% below 103, then what's the probability that that infant is above 103? 100 minus 58, which is going to be 42%. Okay? I want to see smiles out there so we understand it. Okay, what's the next problem here? What's the probability that the infant's PDI score is between 97 and 103? Well, this is interesting. So now we're looking at 90. Whoops, I should have used the pen for that, right? Undo that. Okay. Let's see. Let's say that this score is 97. Okay, well, that's going to be, let's see what the z-score is for that. Z is equal to x minus mu over sigma. So it's going to be 97 minus 100 over 15. That's equal to minus 3 over 15. And that's equal to negative 0.2. Right? So we're going to be on the other side of that table. Let's go to the table. And we go to the table. And negative 0.2, negative 0.20 is about 42%. 0.20, 42%. If it were 0.24, we'd be over here. Right? But negative 0.20 is 42%. I'm going to go back here. So this area is 42%. From this area down is 42%. Right? And we know that this area down, right, was 58%. Right? So if I take my area, which is 58%, everything from here down, and I subtract the 42%, it'll leave me with the area that's between 97 and 103. 58 minus 42 is 16% of this population is going to have a PDI score between 97 and 103. Okay? Find the PDI score for a PDI. Would you be surprised to see a value of 90? How many standard deviations below the mean is 90? It's not even one standard deviation below the mean, right? That's pretty common, right? Once that, we said that at least one standard deviation below the mean would leave about 16% of the population. So it wouldn't be that common, but it certainly wouldn't be rare. It happens one standard one standard deviation below the mean or more below the mean 16% of the time. So not so rare. Okay, community response time. Okay, this one's a little funky. It involves the Poisson distribution. I wouldn't worry about this problem for your exam. Not time. Maybe not. Let's see. Yeah, that was. Yeah, let me skip that one. I just easily take that. Okay, let's move on to diagnostic tests. That gives people a lot of trouble also. Suppose that there was a diagnostic test for prostate cancer that was 95% accurate, both on men and both on those men who did, and those men who did not have the disease. In other words, the sensitivity and specificity are 95%. If 40% of the men in the population have prostate cancer, that might be realistic for a population, say, over 70 or 80. Right? I think there are some statistics that 80% of men over 80 have prostate cancer cells that are detectable. But usually there's such a slow growing form of cancer that they don't bother to treat it, because over 80 they figure they'll die from something else before they would die of that very slow and non-aggressive form of, mostly non-aggressive form of cancer. Although now they're better at differentiating really aggressive ones from non-aggressive. So let's take a look at that on Excel. I'm going to create an Excel table. Okay, let me blow this up a little bit more. Okay. How did I do that? Tell you what. Let me add another sheet here and work here. And I'm going to go here. And spread it out a little bit. And then I'm going to go here. Make this a bit wider. Okay, good. So I'm going to make up a table here. And this table is going to represent the results of the diagnostic test. They tested positive or they tested negative. And it's going to include also whether a person has that disease or not, B positive or B negative. Okay. And I'm going to blow these numbers up a little bit. I'm going to center this, and then I'm going to increase the file size. Like so, okay, good. So let's take a look at this. So now, the total number of people, let's do that in this population, compute the probability that a tested patient has prostate cancer, given that its test result indicates so. Compute the negative predictive value for the test. The first thing is asking you for the positive predictive value. I'll explain that in a second. The second one is asking for the negative predictive value. So I'm going to create a version of this population. I'm going to say that there's 1,000 people in this population. I'm going to create something a table that reflects this population. If 1,000 people are in this population that we test, and it's a 40% prevalence, how many people? I'm sorry, 40% prevalence. How many people out of 1,000 would have prostate cancer? Right? Everybody agree with that? 440% out of 1,000. Good. That would leave 600 people in this elderly population that doesn't have any form of prostate cancer at all. Okay. So if the sensitivity of the test is 95%, the specificity of the test is 95%, and the prevalence of the population, I might as well put it down here, it's 10%. I'm sorry, 40%. Okay, again, unusual, very elderly population, this is maybe not so far along. Okay, what does the sensitivity mean? It means how good is it at identifying people that have the disease? They have the disease. How good is it saying, oh, it's a positive test that person has the disease? So if 400 people have the disease in this population and we test them, how many people are going to be here, are going to test positive? 380, 95% of them. I'm going to do it this way. This times 95%, 0.95. Okay, 380 people. That leaves how many people that it gets wrong? 20. And that 20, what's the name for that? I'm gonna ask you true positive, true negative, false positive, false negative. What those are? Those are, again, false negatives. They're negative, but they don't have the disease. They have the disease, but excuse me, they have the disease, but they tested negative. So they're false negatives, okay? These are true positives, okay? So let's take a look at people that don't have the disease. It's also 95% accurate, but there's more of them. So in here, it's going to be 600 times 95%. Was that 570 or something like that? 540. Okay. So how many people that don't have the disease test positive? That's 160, right? So what is 540? 540 is true negatives. What is 60? First of all, what are they? They don't have the disease, but they tested positive. They're false positive, okay? Just so we're clear on this. True positives, right? False negatives, false positives, and true negatives. Blow them up, enter them, and blow them up. There we go. Okay, that's mirrored here. Okay, so how many people tested positive? 445, exactly. How many people tested negative? Let me do this a different way. It's going to come up later. It's going to come up later. Okay. Equals the sum of these two. This. Okay, and this is the sum of those. How many people tested negative? It's equal to this plus this. And that should add up to 1,000, and it does. Okay, great. So now, if you test positive, what's the probability that you actually have the disease? How many people tested positive? And how many of them actually have the disease out of those? Right. So it's 380 divided by 140, or you're 86% certain to have the disease. Probability you have the disease is 86%. Okay, let's say you test negative. What's the probability? How many people tested negative? 560, right? What's the probability you don't have the disease if you test negative? Well, the number of people out of those 560 that don't have the disease is 540 over the total number of people who test negative is 96%. If you test negative, 96% chance you don't have the disease. If you test positive, 86% you have it. So 14% chance you don't have it. Let's change something very important. Let's change the prevalence. I'm not going to change the sensitivity. It's the same test, but we're going to apply it to men that are in their 40s. Okay, men that are in their 40s, the prevalence might only be maybe, I don't know, what do you think? 5%? Less? 5%? I'm going to call it 5%. Okay, 5% of 1,000, 50 people, right? 15. That means that 47.5 of them will correctly be identified as having the disease. They'll be true positive. 20% will be false negative. 20 will be false. That's not right. Equals 50 minus 47. Yeah. Right. It gets it right 95% of the time. 47.5. The false positives are 2.5. I could have made this so it was whole numbers, but it really doesn't matter. Okay, so how about it's a 1% prevalence, right? So that means that instead of 50 here, we have 950 people. Right? So 855 of them, and this is going to be equal to 950 minus 855, 95. So that should add up. And these should add up as well. And they do, as a matter of fact. Okay, so what happened here? Same test. 95% of the time it got it right. 95% of the time they got the negatives right, right? But this time, let's take a look at what happened to the predictive values. If you tested, how many people tested positive? 142. How many people actually have the disease that tested positive? 47.5. So that's equal to 47.5 divided by 142.5, and it comes out to be 33%. Exactly the same test applied to a different population came out to be only, something happened. Oh, because I linked it up there. That was 86%. The predictive value, the positive predictive value, the likelihood you had the disease if you tested positive goes way down. Only thing that changed in these populations was the prevalence. The important thing about diagnostic tests. That's why there's always a debate when people say, hey, we should start screening all men at 40 for prostate cancer. The problem with that is that age, it's a relatively low prevalence. And that means you're going to get a lot of false positives. But you're going to need a lot of money going out of the healthcare system into that for people that may not need it, so on and so forth. More invasive tests, biopsies, things like that. Okay. So that negative predictive value, just so you know how to calculate the negative predictive value, it's equal to the number of people that are true negatives, right, divided by the total number of people that tested negative. So it's the false negatives and the true negatives together, so that's going to be 99. Now, there is a formula you can use based on Bayes' theorem, this idea of conditional probability. There's a formula you can use. I'm going to finish up with this. Okay. Guys online are very relatively silent there. I don't know what that is. Hope they're awake. Normally I get a little chatter on there. You guys are still there, right? Okay. Oh, no, I got a beach ball. I guess this is, what is this, the 20th anniversary of Google? Is that what that is about? Let's see. Positive predictive value formula. Okay, let's see if I can come up with it quickly. I know I have it somewhere in my stuff here, but here we go. I'm going to take this formula. I'm going to drag it in here if I can. Oh no, it's copied. I have to drag it onto the desktop first. Where'd it go? There it is. Okay, now I think I can drag it in here. Okay. Work with it. I want it in the background here so we can read it. Why is that not cooperating? There we go. Here it is. Okay, so there's the formula here. The sensitivity times positive value is equal to sensitivity times the prevalence. In other words, the prevalence is the percentage of people, a proportion in the population that have the disease. So that's the proportion of people, percentage of people that have the disease, the prevalence, times the sensitivity, which tells you how good it is at predicting that. So that's really the total number of the proportion of true positives. So at the top, we got true positives. Then we got true positives down here again. So since we know it's got to be the number of true positives over the total number of positives, which is the true positives, plus the false positives. So this must be the false positives, right? Then we add them together and we get the positive value In fact, it is. It's 1 minus the specificity, which is the percentage of people that that don't have the disease, times 1 minus the proportion of how good it is at they're doing positive, which is the percentage that it gets it wrong on people that don't have the disease. So that actually is the false positive. So it's a true positive. Just like we use that chart, this formula is really doing the same thing. So I'm going to do it for the second formula, second thing that we came up with, which was the sensitivity. What was the sensitivity again? It was 0.95 times the prevalence, which I said was 5%, 0.05.
For the 40 year.
No, I was going to do the second one. What did I say for the second one?
40 year,
5%. Okay, good. So that proportion. Oops. We need to put my asterisk in there. That's 0.05. Okay, it's 0.07. So the bottom part of this formula is going to be equal to the same thing as that, plus it's going to be equal to 1 minus the sensitivity. Sensitivity was 90%, so it's going to be 0.05, 95% minus 1 is 0.05, times the prevalence, well, times 1 minus the prevalence. The prevalence was 5% also. Am I right about that? Yes? Yep. No, hang on. So 1 minus the sensitivity, yes. 1 minus sensitivity, 1 minus the prevalence, times 1 minus the prevalence, which is 0.05, which is 1 minus the prevalence, which is 0.95. Okay. I don't know why it's asking me that. Yes. Yeah, don't worry about that. Okay. So what does that turn out to be? It turns out to be, this is on top, right? Divided by the sum of these two elements that are on the bottom. Put parentheses, this plus this, enter, and we, oops, something like
You forgot to multiply 1 minus the
that.
You can do the 1 minus p.
1 minus, did I get the 1 minus p wrong?
You forgot to put 1 minus 6.
1 minus, 1 minus p. Did I do that? I'm going to do this again. This is right, that one. Okay, so now this is equal to 1 minus the specificity, which is 0.05, right? 95%, 0.05, times 1 minus the prevalence, which was 5%, which is 0.95. You know something's wrong there. Sensitivity. Yeah, it's 50%. I thought we came up with a different number. You know, I don't have it anymore, do I? Maybe I got this wrong. 1,000. This turned out to be 50, 47. That looks right. 95. Is this right? This is. Oh no, I got it wrong here. This should have been 0.5, 0.95. Turns out to be 50%, not 33%. So yeah, this formula didn't do it correctly. I forgot that this prevalence was, I was saying was in that second example was 5%, but I used 10% when I calculated the negative predictive value. So they both agree, 5% and 5%. Okay, so let's call it a night. I'm going to